Hey, good afternoon. Right, so before we proceed with today's discussion, let's do a recap of what we have covered last time. So, can anyone share what they've learned from last week's discussion? Again, can anyone recall any insights or concepts from last week's meeting? Yes, Mr. Muti, please proceed.
Ano po, na-discuss po natin yung mga sumunod po sa bisection method, which is yung false position method, and then fixed point, tsaka po yung Newton Raphson po ata yun. Hindi ko po matanda ng ayos.
All right, thank you. No, so last time we have covered the continuation of the methods for finding roots. Mainly includes the bracketing or close methods and the open methods. No, so thank you. And today we will continue with the open methods, beginning with the secant method. So this is a recursive method for finding the root for the polynomials by successive approximation. It is somewhat similar to the false position method in principle, but here we do not need to follow yung Bolzano's theorem, no? Where we need to check for the signs of the values of the function for each iteration. And unlike the Newton-Raphson method, here we do not need to differentiate. So this does not require knowledge of calculus, no, for the given function. Okay, so to begin, let's try to recall what we have covered last time. So we have the Newton's method, right? If you've seen the materials last time also, so these were already posted, no, in the file section or in our classroom. So we have the following formula, which is actually based on the Taylor's theorem, no, or Taylor series, where the new solution is based on the previous approximation minus the value of the function and divided by the slope of the function at that point. Okay, so the modification here is that we will use instead the following equation, and this is the first derivative, but this expression allows us to perform something called the incremental analysis, no, where uh, where we have this as the slope, the slope of the function expressed as in terms of derivative, no. Now the derivative of the function at that point, right, can be expressed as the following, which provides the slope, no. So the distance between the point itself and another reference point. So this is maybe around slightly left of that uh, reference point, and this is your vertical dimension divided by the horizontal changes, right? And so we have the slope in this expression already, and this provides the slope as an equivalent to the derivative of the function at that point. And so what we're gonna do is just plug in this equation into the previous equation we've used for the Newton's Raphton method, and so we can get rid of the need for differentiating the function, no, as stated in this denominator. So here we can obtain the solution directly with only the knowledge of the function itself that we were working with. Okay, so the process will look like this, no? So if we have the function f of x, then we have to equate that to 0, and then we have to make initial guess at x0 and x1, and then perform this calculation, no, the previous formula that we have for each iteration. And then we repeat the process until we reach either of the convergence criterion. Okay, so we can provide, or we need at least two convergence criterion for this. And the first one is fixing beforehand, no, a maximum number of iterations that our program needs to perform. Otherwise, it will terminate itself, or a test condition where this thing is actually your error, no. So once you've reached that tolerance limit, once you were able to arrive at an error value lower than the predefined limit, then the program also will terminate itself. All right, so we can construct a code based on the said process. Following that algorithm, a pseudocode can be constructed as follows. So you can expect, no, the process that goes through when we try to automate the process of calculation using the secant method. All right, so first is that we have to make an initial guess for values of x0 and x1, and then define the um, amount of tolerable error and the number of iteration. So we initialize the program and then perform these following loop. No? That if ever the value of the function at point 0 and point 1 is the same, so what does that mean? So it means that the slope between these 2 points is 0. In such cases, if it ever happens, then our calculation will fail, because if you go back to the formula, we have these two values in our denominator. Right? So if this is both 0, then the entire formula will fail to solve for a real value, no, for your solution. So we have to check on that and produce an error notification if that happens. And otherwise, then we're good to go and proceed with the calculation. Right, so the calculation is based on the previous stated formula. Again, this is originally from the Newton's method. So we have the new solution based on the previous one minus, no, the modified slope equation. And then for each step, we will replace the x0 with the new value of x1, and then the x1 will be replaced by the new value of x2, and then we increment the process, and then we command the entire process to stop once it reach the predefined maximum number of iterations, and say that this is not convergent, because if it is convergent, it would have stopped when it went below the allowable tolerance limit here. And then we display the x2 as our solution, and the entire sequence. No? So here's a more intuitive uh, demonstration of how the algorithm works. So let's consider the following function plotted in the red graph right there. So for our initial guess at x0 and x1, we have the projected a straight line in between those 2 points. No? So that's our first secant line in our first iteration. So since you have the value of x0 and x1, you can have the value of f of x at points 0 and 1 also. And you can have the formula for the equation of the straight line. And so based on that straight line, you now have a second solution. As we can recall, solution is defined as the point of intersection, right? So the new solution x2 right here will become new reference point for the next iteration. And so the value of the function at x2 will be somewhere here, no? If we can imaginary project a straight line going here. So the next secant line will be projected between these 2 points, which is, as you can imagine, which is supposed to be closer to the actual solution alpha in there. All right. Okay. So is that demonstration clear for everyone? Okay, so any questions so far? No, you can just post your no, your comments in the chat box if there's any sort of confusion, no, so we can clarify these things. No? Okay, so but in this particular example, you can notice na like in the previous problems no, where we have the bracketing methods, the solution is contained here in the initial interval. Now again, as I've mentioned, the secant method is one of the open methods, so we are not necessarily confined to work under such conditions. And so for example, in this second graph, yan, we have a roughly similar function. But in this case, we have an initial guess of x0 and x1, which is outside or where the actual solution is outside that initial interval. All right, so this is the other case, no? Okay, so what you can see here is that for the first iteration, we have projected a secant line from x0 and x1 and come up with the new solution at x2 right here. No? So in the next iteration, the new solution will be projected from here onto this point that corresponds to x2. And if you can imaginarily project a second secant line from x1 and x2, then should be somewhat closer to x, to the actual solution alpha right here. Right, so hope this demonstration provides an example of how powerful this method is, in a sense that we do not really need to know where the solution is. So just need to keep performing iterations until the error decreases or converges at some value, right? Okay, so in like any open methods, the convergence rate for this technique is relatively faster, no? However, as a drawback, it's not always the case that we may be able to find the solution. Take for example the following graph, so plotted again in red here, and we have an initial guess at x0 and x1 right here now. So the first secant line is projected in between those 2 points, and after the first iteration, we have a new solution x2 right here. Okay. All right. So now in the second solution, or in the second iteration, because in the second iteration, we will have to plot a second secant line going from x1 to x2. So it should be here. If we extend that, we have a new solution at x3 right here. But what you can notice is that in this case, instead of going into the desired solution, which is should be here, we have arrived at a new solution which is further away from the actual solution, in contrast or comparison with x2. So this is a case, right? So this is the case where the new or the secant method will not converge. No, again, this is another drawback, as I've mentioned, when we're trying to use Okay, so when we're trying to use open methods, no? So it's not, there's no, not always a guarantee that we will be able to home in on a solution. Right, so consider, for example, now let's try to work on some problem here that we will solve for the square root of 2, right? So the following equation, x squared minus 2. You just plug in the original equation we've seen from the previous slide. And so the equation remains here now in this section. Okay, so right, and then the equation can be further simplified in the following. Now, working on some reference interval, so let's make an initial guess of x0 at 1 and x1 at 2. Yeah, because in this problem, we're pretty sure that the square root of 2 lies somewhere between those two, no? Or within that interval. So you just plug in the values of 1 and 2 for the first iteration. So for the first iteration, we have the value of x2 at 4 thirds, or this, or equivalent to 1.3. And the second iteration will be using the value of 4 thirds and 2 right here now. So we'll be using the value of x2 and x1 for x3. And so we have 7/5. Well, for the third iteration, to solve for the value of x4, we'll be using the value of x3 and x2, or the 7/5 from here and the 4 thirds from here. And so we have the new solution right here. And if we try to use calculator, this is actually very close already to the actual figure that will be provided in the calculators. Okay, so is the previous example clear for everyone? Any questions so far before we proceed with the example or sample implementation using a spreadsheet? So we're gonna use spreadsheet for this as well. All right, so here is an example of Excel implementation of the same problem, no? So for our initial guess, we have 1 and 2, and then we just plug in the values of x sub 1 and x sub 2. In this case, I use the notation xa and xb, but please don't get confused now. This is the first and second interval, and the new solution is at xe right here. And then we use the same formula as this one for the new solution, right? And so we can solve the new solution will serve as the uh, xb, no, in the next iteration. So xb will become xa in the next iteration as well. So for the relative error, we can use this one. So we can compare x3 and x2, or x2 and x1. Usually we can start already here now, that by using this two figures right here now, so we can already solve for the relative error, right? And then we'll just multiply everything here by 100%. Okay, so fairly simple, no? So we'll just need three columns for the solution at least, and then you have the rest of the error calculations. In some cases, if you're checking for some solutions online, others perform checking by this, no, just plugging in the actual value, and going into the original equation and checking to see if it balances out. Once it balances the equation, then it means that we already reach convergence at that point. So once it reaches zero value, so we can say that this already converge. But in our case, no, in our programs, that will just define the relative error, or percent error. So in most of your p sets, then you at least need to solve for error rates lower than 1%. In many cases, you can use the absolute value function. Now, if you're having issues, or sorry, should be the other way. If you're having issues with the less than, or greater than, no, for the programming side, so you can now have the positive values only after that. Okay, right? So the positive values will be retained after the absolute value operation, right? So again, in this case, 1% error was reached after third or so iterations, and then by checking itself, no, in the original formula, it was zeroed in the fifth iteration. Anyway, I'll just hide this one, to avoid confusion. So we'll just work on the tolerance values in terms of the percent error. Okay, so is this clear for everyone? Any questions or concerns? Okay, so maybe guys, you can work on the same problem, no, as your exercise. Anyway, you'll be doing p-sets later, and so if you can be able to create the same template, then the p-sets will not be a problem. All right. Okay, so let's try to work on same problem for you guys, no? So all right, so I posted the problem in the chat box, so that using the secant method, you'll be solving for the square root of 415 using spreadsheets, no? And you can post your answers in the chat box, uh, and share with us how many iterations it requires, no, to reach an error rate lower than 1%. Okay, so are we okay with this? Okay, so you can use a reference starting with x0 uh, 0 and x1 or xb depending on your templates at 415. Okay, so you can use this as your reference point. So I'll wait for your answers in the chat box. Now, please share how many iterations you were able to perform to reach error rates lower than 1%. Please, if you have any questions, just post it in the chat box now so you can address any sort of confusion if there's any. Okay, so any answers so far? Right, thank you. And well done, huh, for those who were able to attempt. So around 9 or 10 iterations, and similar to the other methods that we've covered. No, the closer is our initial guess is to the actual value, then we will be needing fewer amount of iterations, no, to arrive at our solutions. Okay, so you'll be doing somewhat similar problem for your next P set, which I will post that one after our session. So another P set using Excel for the secant method. Okay, so are there any questions, concerns, or clarifications so far? Let's say if none, can I see a show of hands if everything is clear up to this point? Okay, thank you. So we move on now to our next topic, which is the modified secant method. As earlier, we've recalled or we've seen the technique, no, where the Newton's method was replaced with these equation, and then it was narrowed or eliminated the derivative portion in this denominator. So we have the secant method. In the modified secant method, there's some small changes, no? That instead of the substitution, we only need a point here, a reference point x sub n, and then we will introduce a small perturbation fraction delta here. So it can be a decimal figure around zero point 0.1 or zero point 0.01 or zero point 0.001. And then we will similarly perform some sort of incremental analysis. So what happens here is that you have a width of a very small horizontal value here, and then we inspect the resulting vertical change, you know, so that the overall change in slope with that very small increment in the change of horizontal value. So that's a form of an incremental analysis. So instead, this equation here will be introduced into the original formula from the Newton-Raphson's method, no? Which is again based on the Taylor's series. So we plug in this expression equivalent to f prime, and so we now have the new formula in this step. Okay, so let's try to demonstrate this using a different problem here. Okay, so we want to solve for the root of this function here, e to the negative x minus x, starting with an initial guess of 1 and the perturbation fraction delta at 0.01. So in this case, we only need to assume or make one guess, no, for the x0, starting with 1. Then we evaluate the value of the function, this one, at that point, and then we have the following. No? So here's the where the incremental analysis starts. That from a reference point x0, we move a little further to the right, at 1.01, and then we expect, or we inspect rather, the changes in vertical value. So the negative 0.632 here becomes negative 0.645 right here. Okay, so the corresponding change, 1% change in horizontal value resulted to these changes in vertical value. And then we have the previous formula. We just plug in all the values in the formula, and so we have the new solution at x1 equivalent to 0.53726, right? Is are the steps being followed? So the procedure is pretty straightforward. You just have to uh, recall this formula here, no? And then everything will be evaluated with a small perturbation fraction. And so once we have the new value of x after the first iteration, we make use of this for the second iteration, just like in the Newton's method. No, we now have x1 here. Then we again evaluate the value of the function at that point. So we have this one and perform incremental analysis on the horizontal dimension. So we have x plus 1 at 0.54. No? Then the corresponding change in the vertical dimension is this one. So it sort of increase a little, or decrease rather, no? So for point from 0.47 it decreased to 0.38 right here. Okay, so once we already have all these values, then we just plug in all these figures into the same equation. And so we now have the new value of x after the second iteration. So similarly, we can calculate the error figures here, right? Okay, so we move on to the next iteration. So here we just repeat the process, no, for the third iteration. Make use of the previous value of x from the second iteration. We evaluate the value of the function at that point. So it becomes somewhat close to zero. We perform incremental analysis, so this point moves further to the right in a very little step. And then we check for changes in the vertical value. So it sort of cross the x-axis and they're negative here. And then again, we plug in all these values into the equation here. And then we now have the new solution right here. So similarly, for the error calculation, we'll make use of the previous formulas that we have. Okay, so we will try to implement the same using spreadsheet, but are there any questions, concerns, or clarification so far? Okay, so if none, can I see a show of hands if everything is clear up to this point? Right, thank you. So let's move to our example here, right? So this is the same problem. No, we will implement this in spreadsheet. Okay, so yeah, so for our initial guess, we have the value of 1 and then the perturbation fraction at 0.01 here. And so the incremental movement at x is this one, no? So delta times x sub n. And then we add this together, no? So we have to add this to check for the incremental movement. So the value of the function at the initial guess is provided here. So it's the same equation, e raised to negative x minus x. Similarly, we'll use the original function to evaluate the point after the incremental movement, after the introduction of perturbation fraction here. And so the new solution after the first iteration will be this one, right? Okay, so yeah, so you have this equation here. You just plug in everything into this equation. And so the new estimate is at 0.573. The error percent is 56, no? Because of you just made a guess here. And so after the first iteration, you have the following. But you can see that this is able to diminish rapidly. So we're expecting 1% or less than 1% after the third iteration here, no? If we try to project this, but I want you guys to do this as your exercise. I've added the separate column here, and this is the error in ppm or parts per million. So in your assignment, I'm sure you've noticed that we have different error calculations. The percent, the fraction of 1,000 is the per mil value, and when you try to multiply this by a million, then that's the ppm value or parts per million. Okay, so I'd like you guys to work on the same problem, but I want you to figure how many iterations does it require for the modified secant method to arrive at a solution with an error rate of less than 1 ppm. Okay, so can you work on that? I'll post the same problem in the chat box. So this case, this is the modified secant method. You have to solve for the same problem, no? Square root of 415 in spreadsheets and come up with the number of terms required to arrive at an estimates or approximation with error less than 1 ppm. If you have questions, concerns, or if you need further clarifications, just post your comments in the chat box. Okay, any answers so far? Right. Any attempts so far? All right. Any other attempts? Clarification of the problem pala should be 415, no? If you've seen in the chat box. So anyway, if you work on this problem, I should have switched it earlier, no? So if you work on this problem, 1 ppm is reached at 6 iteration. So for the square root of 415, so you just have to replace this thing, no? With 415, same as this one, and then we'll just repeat the process. So 1 ppm was reached. So this is 1%. So we'll so I'll hide this. This is another way of checking and the solution, that if again the previous function, the same function matches the previous one, then you'll just check how many iterations it take to alpha, and it return to a bigger amount, or sorry, this should be uh, this one, no? So this is the new solution. Okay, so it's supposed to reach zero anytime soon. Or it's able to calculate still. So anyway, we're expecting this to come up with a lower value. Right, so for the ppm error, so we'll just multiply the same with with 1 million. So we have the relative error here. Then we will multiply this by 1 million. So 6 zeros, no? So yeah. And yeah, so after seventh, eighth, or ninth iterations, ninth, no, if you include the zero iteration here, then we're able to reach convergence, no, for that particular problem. Okay, thank you guys. Right, so again, you'll be working on some similar problems for your another P set, no? So there will be 3 P sets. Another one will be the next topic, no, that I will present. Right. So, are there any questions, concerns, or clarifications so far? Yes. Please proceed.
Sir, dun po sa delta lagi po yung 0.01.
That's the usual, no, in the textbooks, no. But if you want to experiment, this should be small value, eh. So let's say 1. Uh, in some cases, it did not affect the rates of convergence when I tried uh, 0.1, no? Or it should be standard. Or if you even try for a very small value of increment like that, no? Either way, will still arrive at okay. So somehow it can affect the rates of convergence, no? We try to go back just to compare now. Here we have ninth iteration as compared to previously we only have eight iteration. So but not that much, no. So you can use yun. So for the p sets, it will be defined. But for experimental reasons, you can use any reasonable number, no. Anyway, you know naman that the goal is to have the solution here to converge at some fixed value, and that the error should be a diminishing figure as you go along or as you increase the number of iterations. Okay, so this one is somewhat a conservative value, but you can play around this, no? So if you have created templates, then you can try to play around that stuff. But there are some implications on the results or the number of iterations. But if there's anything that can significantly reduce the amount of calculation, is that if we have an initial value or initial guess that is supposedly close enough or closer to the actual solution, then we can guarantee that shorter amount of calculation time is required, no, compared to when we have an initial guess which is further away from the actual solution that we are solving for. Okay, so I hope that contributed